This is the third video on the solution to problem 51 in our textbook. In the previous two videos, we have shown that 0 is an accumulation point for the set M, which is the set of reciprocals of the natural numbers. And we have shown that if a point is less than 0 or bigger than 1, it cannot be an accumulation point. So in this video, we're going to finish off the case that says if A is not equal to 0, then A is not an accumulation point for the set M. So we are now looking at case 3. And what we're wanting to do is we want to let A be any number that is strictly bigger than 0 and less than or equal to 1. And we need to show that A is not an accumulation point for the set M. Now, I want to actually break this into 3 sub-cases. So right now, what I want to be thinking about is a very special sub-case. What happens if A is actually equal to 1? Well, let's draw a number line. So here's my number line. And let's see, here's 0, and here's 1. And what I'm going to do is I'm going to remember that M is the set of reciprocals of the natural numbers. And we can start plotting these guys, and so let's plot them. We know that 1 is inside N. We know that 1/2 is inside N. We know that 1/3 is inside set M, and so on. And what I want to notice from this particular number line is the following observation. And let me get my handwriting a little bit better. I know that 1 is inside M, and I know that all other elements of M are less than or equal to 1/2. And so what that means is that if I let delta equal 1/4, then the delta ball centered at 1 of radius 1/4 looks like this. So that's that delta ball. And this particular delta ball intersected with the set M contains only the element 1, because all of the rest of the elements of set M are down here. And so they're not inside this delta ball. So what does that mean? Well, that means that if I look at the intersection of the punctured delta ball, centered at 1 of radius 1/4, and I intersect it with the set M, that is going to be the empty set, because it's important to realize that the punctured ball would look like this. Here's 1. And this would be 3/4, and this would be 5/4. And since I am puncturing it, I no longer have that element inside the punctured ball. And there are no elements of M that lie in that particular interval. So there are no elements of M in the green part. And what does that mean? That means 1 is not an accumulation point for our set. Well, okay, let's now look at the second subcase. So, subcase 2. And in subcase 2, we're going to assume that A is strictly between 0 and 1, and A belongs to the set M. So what that means is that A is equal to 1 over capital N for some capital N that is bigger than or equal to 2, and capital N is a natural number. Now, that means the following. We have this kind of a situation on our number line. Here is our number line, and we have 0 here, and we have 1 here, and we have 1 over capital N, which is equal to A here. Now, I also want to be thinking about this. I know that capital N is smaller than N plus 1, and it's bigger than N minus 1, and N minus 1 is bigger than or equal to 1. And that will imply that 1 over N is bigger than 1 over N plus 1, and it is smaller than 1 over N minus 1, and 1 over N minus 1 is less than or equal to 1. So we have this particular inequality. And I want to put that on my number line. What this inequality says is that 1 over N lives on this side of A, and 1 over N plus 1 lives on that side. And because there are no natural numbers between N minus 1 and between N and N plus 1, I know that there are no elements of set M in this range, with the exception of A. In other words, I know that if I look at the punctured ball, so I'm going to delete this, and I'm just going to pick a delta that is smaller than the distance between 1 over N and these two fractions, there's not going to be any elements of set capital M in that particular delta ball. Now, to rigorously prove this, what I'm going to do is I want to let delta be bigger than 0, and I want delta to be, and let me correct my handwriting, I want delta to be less than the minimum distance between A and these other two fractions. So it's going to be the minimum, it's going to be less than the minimum of 1 over N minus 1 minus 1 over N. And let me correct my handwriting. And it's also going to be less than 1 over N minus 1 over N plus 1. So that means the delta ball centered at 1 over N of radius delta has no elements inside set M except for A, which is equal to 1 over N. In other words, when I look at the delta ball, I've got this sort of a situation. Here is A. Here is A, which is 1 over N. I have the delta ball, so this distance is delta. So that's my delta ball, centered at A of radius delta. And outside of that radius delta ball, on this side is 1 over N minus 1, and on this side is 1 over N plus 1. And because of the way the integers work, there are no elements in the punctured delta ball inside set M that lie in here. So no element of set M lies inside the punctured delta ball. And that says that 1 over N is not an accumulation point. for my set, capital M. Well, we have one last case to deal with, and so let's look at that subcase. Our third subcase is A is between 0 and 1, and A is not inside set M at all. Now, what I want to do here is I want to think about the Archimedean principle. The Archimedean principle, well, actually, I want to talk about reciprocals first, so let me get the reciprocal stuff in there. What I want to do is I want to notice that 0 less than A less than 1 is going to imply that 1 over A is strictly bigger than 1. And then the Archimedean principle is going to kick in and say that there exists a capital N inside the natural numbers such that 1 over A is trapped between capital N and capital N plus 1, and it might be equal to capital N, but capital N is known to be strictly bigger than, well, it's bigger than or equal to 1. But what I want to notice is something else. If 1 over A was actually equal to capital N, then A would be equal to 1 over N, and it would be actually inside our set M. So that means we can safely assume that we have this particular inequality. N is less than 1 over A, and 1 over A is less than N plus 1. Well, that's going to imply that 1 over N is bigger than 1 over 1 over A, which is bigger than 1 over N plus 1. And that will imply that 1 over N is bigger than A is bigger than 1 over N plus 1. And I can draw a picture of that. Here's our number line. There's the number line. We have A here. We have 1 over N here, and we have 1 over N plus 1. And again, it's easy to see that we can pick delta to be the minimum of the distance between A and these two fractions. So it will be the minimum of A minus this fraction and 1 over N minus A. Delta needs to be less than that minimum. So let me correct that. And if I pick delta to be anything that's less than that and bigger than 0, then what I've got is a delta ball that looks like this. And A, of course, is not in M. And these two guys, there's no element of M that's between these two fractions. So it turns out that there is no element of M inside that delta ball. So because there is no element of M that lies between the fractions 1 over capital N and 1 over capital N plus 1, we know that the delta ball centered at A of radius delta intersected with the set M is going to be empty. And that will say that A is not an accumulation point for set M. And that actually completes the proof for problem 15. In other words, we have now shown two things. 0 is an accumulation point, and if A is not 0, then A is not an accumulation point. And that completes the proof of 15, of problem 51.